inverse function in terms of stuff you've done many times before. How do you undo doubling? Well, by halving. If somebody doubles something, you can just cut it in half and it's back to what it was before. How do you undo adding 3? By subtracting 3. Well, how do we express this in functional notation? First of all, the doubling function is f of x equals 2x. That is, it takes 1 to 2, 2 to 4, 3 to 6. So the inverse function is the thing that reverses that. So it's got to take 2 back to 1, 4 back to 2, and 6 back to 3. And so we have a special notation for that. F to the minus 1 of x equals x over 2. That's the halving function. It undoes the doubling function. Now this little sign right there, though, I said to the negative 1 power, don't think of it as negative 1 power anymore. This is an unfortunate choice of notation for inverse, but that's been the standard for a long time. This little negative 1 above the f means the inverse function of f. It does not mean 1 over x. So get that down, kids. X. Okay, key idea here. This negative 1 power does not actually mean raise it to the negative 1. It actually means inverse. Now, let's look at this next one. How do you undo adding 3? Well, let's look at it as a function now. F of x equals x plus 3. That's the adding 3 function. So the subtracting 3 function should be is x minus 3. And those functions undo each other. Now the function, the composition of a function and its inverse should make the identity function. That is, f of f inverse of x should equal x, and f inverse of f of x should equal x. Let's look at that with our last example here with f of x. So when we do f of f inverse of x on this function, that would be f of x over 2, but the f function is to double it. So it's twice x over 2, and we get x. Notice if we do the composition in the other direction, we still get the same thing. That is, f inverse of f of x is f inverse of f of x, which is 2x. And now you put 2x in the f inverse function. 2x divided by 2 is x. Okay? What is the inverse of fx equals 2x plus 3? Is it 1 half x minus 3? Because certainly the doubling function is inverted by 1 half x. The adding 3 function is inverted by subtracting 3. But the problem is, let's check this in terms of our f inverse of f of x. If that's the case, if f inverse of x equals 1 half x minus 3, then let's look at f of f inverse of x. We get f of 1 half x minus 3. So now putting that in the f function, that's twice 1 half x plus minus 3 plus 3. Hold it. X minus 6 plus 3 equals x minus 3. Oops. So this is not the inverse. These are not inverses. You've got to get the composition of the two functions to equal x for them to be inverses. And let's see where we went wrong. Okay, here's a picture of a man who's had a long day of work at the chemical factory. And he wants to enjoy his nice skim milk here. But the problem is, he's got this mask on. He's got to recall, what happened in the morning? In the morning, I put on mask, and then I put on hat. Now what happens in the evening? In the evening he has to reverse those things. But he can't take off the mask because the hat's on. So he has to take off hat. And then take off mask. Do you see how the inverse operations have been done, but they've been done in the reverse order? Okay? That applies to what we were trying with the function f of x equals 2x plus 3. The function f of x equals 2x plus 3 is a composition of two functions, doubling and then adding 3. So when we do the inverse functions, we have to do the inverse of each of these, but in reverse order. So f inverse of x will be subtract 3, then have. So f inverse of x should equal x minus 3 all over 2. Let's see how this works with our composition now. Okay, here are our two functions again. F of x equals 2x plus 3. And I want to show you that f inverse of x is x minus 3 all over 2. So to do the composition, it's f of f inverse, which is x minus 3 over 2. And then we put that into the f function, so it's twice x minus 3 over 2 plus 3, or we get x minus 3 plus 3 equals x. And in the opposite order, we get f inverse of f of x, which is 2x plus 3, and we put that into the f inverse function, so 2x plus 3 goes into minus 3 all over 2, so you get 2x over 2, which is again x. So f of f inverse of x and f inverse of f of x both equal x. So that is the inverse. Now, what I want to show you is that there's an easy way to do this, because sometimes trying to do a bunch of different compositions in reverse order can be confusing. So here's a little trick. When you start with f of x equals 2x plus 3, first think of it as y equals 2x plus 3. Now, I put a little dashed line here to indicate that I am tripping over into inverse land. Inverse land is not the same function. It is the inverse function. So we switch the roles of x and y. We get x equals 2y plus 3. So x minus 3 equals 2y. So x minus 3 over 2 equals y. So therefore, we get the inverse function is x minus 3 over 2. So there's the key idea. When you want to create the equation for an inverse function, first of all, write f of x as y. Then switch the roles of x and y and solve for y. And that will give you your inverse function. Now here's a geometric idea of how you can understand inverse functions. They are mirror images of each other over the line y equals x. And to see this, let's take a look at GeoGebra. I've got the function f of x equals 2x plus 3, and here's the point A on that function. Notice here the y-intercept at 0, 3, and the x-intercept at negative a half, 0. That's the line y equals 2x plus 3. Now, here's the line y equals x, also known as the identity function, because f of x equals x. And we want to reflect the points on our function over this line. Now, an easy way to reflect points over the line is in GeoGebra, you can actually do a reflection. You come over here to this symbol, reflect object about a line, select object to reflect, then the line of reflection. We select A, and then we select this line, and it creates A prime. That's the mirror image of A over A prime. If we grab that point A, you can see that the mirror image slides along with it. And when the original function is 0, 3, the inverse function is at 3, 0. Add A. Now, here's a trick to actually create all the points that make up the inverse function. It's called a locus. It's in your section on intersections or perpendicular lines, on parallel lines, and so forth. You pick locus, and it will create the locus of points. Select the locus point, then point on object. So we've defined A as an object on the line. This is our locus point. So we select the locus point, and now the point A on the object. And there it creates another line. I just made it green to contrast the red original function, and here's the green inverse function. Now, since it's locus of points, GeoGebra will not actually come up with an equation for you, but we can see it's a line. It goes through 3, 0, and through negative a half, and 0, comma negative 1 1/2. So it's going up 1/2 over 3, so that means it has a slope of a half, in contrast to the original line, which had a slope of 2. And that's consistent with what we saw in our equation. Let's look at the equation again. Another way we could write the equation is to say f inverse of x equals x over 2 minus 3 over 2. That's consistent with what we just talked about. The equation had a slope of a half and a y-intercept of negative 3 halves. So far, we found the inverse of fx equals 2x plus 3, and we saw it wasn't just a half x minus 3, it was x minus 3 all over 2, and we also looked at the answer visually. Now let's take on the inverse of f of x equals x cubed minus 4. First, we start by writing as y equals x cubed minus 4, and then we're ready to trip over an inverse line. I put this dashed line to represent the line y equals x that we cross over, that we reflect over, so that you remember that you're not just making an equivalent equation here. This is a different equation. It is the inverse of the original function, because you've switched the roles of x and y. So x plus 4 equals y cubed. So y equals the cube root of x plus 4. Let's look at that as a picture. We see it's like that. Here's the original function, x cubed minus 4 shifted down, and here's its inverse reflected over the axis. Finally, let's take a look at f of x equals x squared minus 1. So we write as y equals x squared minus 1. We get x equals y squared minus 1 when we trip over into inverse land. There we are in inverse land. Well, start solving this. X plus y equals y squared. We take the square root of both sides. Square root of x plus 1 equals the absolute value of y. So you actually get y equals plus or minus the square root of x plus 1. Now, do we want to stop there? As we can see, if we did this, we get an inverse that actually creates something that flunks the vertical line test. Y equals x squared minus 1 is a function, but it flunks the horizontal line test. Flunks the horizontal line test. Now, you probably thought there was only a vertical line test. And that went like this. If a vertical line crossed a relation more than once, it was not a function. Now we have our original parabola, which is a function. It passes the vertical line test. But since the horizontal line in the inverse function would actually turn into a vertical line like this, that vertical line would hit the inverse function twice, making the inverse not a function. So that means we can't really find the inverse of fx equals x squared minus 1. What we have to do is limit the domain of the function, of the original function, so that it can be inverted. And so here we have it. By taking the original function fx equals x squared minus 1, by restricting its domain to x strictly greater than or equal to 0, we only get this right half of the parabola. Now it passes the vertical line test, it's a function, and it passes the horizontal line test, so its inverse will be a function. Its inverse ends up being f inverse of x equals square root of x plus 1. And notice the domain and range switch. The domain here of x greater than or equal to 0 and y greater than or equal to negative 1 has been switched. The roles of x and y have switched here as well. Now it's x is greater than or equal to negative 1 and y is greater than or equal to 0. Right? Flange out.